would like to share you with our work in CVPR23. This paper focuses on instance segmentation on challenging videos. Video instance segmentation, VIS, methods with per clip input often fail on challenging videos with occluded objects or crowded scenes. This is because object queries in these methods depend mainly on object position and categories, which cannot encode discriminative embeddings between objects well, making the query-based segmenter difficult to distinguish those hard instances across frames. To address these issues, we propose to mine discriminative query embeddings, MDQE, to segment occluded instances on challenging videos. This paper includes two major parts: object query initialization and the inter-instance mask repulsion loss. We first outline the proposed MDQE in Figure 1. During training, the features F output from backbone and encoder will be fed into our proposed query initialization module to produce temporally aligned frame-level queries, denoted by circles. After 6 decoder layers, flip-level queries, denoted by squares, will be linearly combined with mask features to produce final instance masks. Finally, the predicted masks are supervised by our proposed inter-instance mask repulsion loss to distance each instance from its nearby non-target objects, implementing contrastive learning of instance masks. Next, query initialization includes 2 steps: grid-guided query selection and interframe query association. The grid-guided query selection aims to select the peak point per grid frame by frame, then assign the coordinates and features of the peak point as the initial positions and content features of the query. To improve temporal consistency, we calculate embedding similarity of queries between adjacent frames to roughly align queries. Finally, the initial query tokens will be input into the decoder layers to decode discriminative query embedding, which can distinguish occluded or crowded objects well across frames. Loss. For each object, we first utilize bounding box IOU to find its nearby objects and then set the union of nearby object masks be the ground truth inter-instance mask. Based on our defined inter-instance masks, we extend traditional binary cross-entropy, BCE, loss and dice loss to the inter-instance BCE and dice loss, respectively. The above loss considers both the matching of pixels belonging to the target instance and the mismatching of pixels belonging to the nearby non-target objects, therefore providing instance discriminative information to the segmenter for producing more accurate instance masks. Next, we test our proposed MDQE on YTBIS21 and OVIS datasets. We explore the performance improvements brought by query initialization. The baseline seek former achieves only 15.4% mask AP. After individually integrating query initialization, O2I, decoder architecture, and temporal cross-attention, the performance significantly increased to 25.6% mask AP. The bottom figure visualizes the query locations produced by our proposed initialization on the challenging videos. Our inter-instance mask repulsion loss brings significant improvements on all occlusion metrics, resulting in better instance segmentation results on challenging videos. The bottom figure displays the visual comparison of instance masks on a video with heavily occluded objects, where the masks are predicted by MDQE with traditional mask supervision loss or inter-instance mask repulsion loss. We explore the VIS results by varying the clip length. The mask AP fluctuates between 30.0% and 31% from 2 frame clips to 7 frame clips. With ResNet 50 backbone, we compare the proposed MDQE with state-of-the-art methods on OVIS and YouTube BIS 2021 datasets. The comparison shows that the proposed MDQE is the first BIS method with per-clip input that achieves state-of-the-art results on challenging videos and competitive performance on simple videos. The following figures show the predicted instance masks obtained from the recently proposed top performance methods on challenging OVIS videos. One can see that compared to idle and min-BIS with per-frame input, our MDQE with per-clip input can exploit richer spatial temporal features of objects, thereby segmenting occluded objects better. Thank you for your attention.